but it was an audio recording. And they would do that to drive the net.
Wait, they would have the man. Wait, the baby would.
The baby would, the baby suckles when it's on. So they would but they do it faster because they can hear their mom's voice. So they would record their mom's voice, and then they would make the babies do. Everything I learned about it makes me want to puke. Does it make sense? I can't say it out loud.
Wait, down there?
Yes. And they would put their mom's voice, and they would suckle faster because that will make them suckle faster because it's their mom's voice.
Yeah. It makes me want to cry.
I cried. I actually cried.
Oh my god.
All right, lock in. Okay, so this reaction, here's the overall at the top. All right, you should be able to knock out intermediates, catalysts, those type of things. That's not what we're looking at right now. All right, I want you to notice this right here. What does that tell me? Well, what do we call that? Equilibrium. It's at equilibrium. This reaction is at equilibrium. When you see the arrows forward and backwards, it tells you it's an equilibrium reaction. So, normally, which one would be our rate determining step? The slow. And that's still true, okay? So, we know that this one is our rate determining. So what would our rate law look like? Knowing that the slow is our rate determining step, so rate equals what? K HgCl2 C2O4 -2 brackets and C2O4 -2 brackets. Does everybody agree with that? Everybody good so far? Okay. Well, because this is here, that tells me that, you see how this is in the products, this is in the reactants? That is actually an intermediate. Now, can an intermediate be part of the rate law? Yes. But it also tells me that it could go in the reverse reaction. It tells me that this is basically, if I go in this direction, is equal to this. Do you agree? Everybody agree with me? Okay. So, if that is my intermediate, I have to go to another piece of paper. I'm so sorry. So, here, I'll just write the rate law. Rate equals K.
We can't see.
C2O4 -2 brackets C2O4 -2. Okay, so there's the original rate we said from the slope. This is from the slope.
Thank you.
But if I go back up to the equilibrium reaction, this is basically equal to brackets HgCl2 C2O4 -2. Do you agree?
Yes.
So what I'm going to do from that, instead of writing this, the rate law is actually rate equals K HgCl2 C2 C2O4 negative 2 and a C2O4 negative 2, which really is rate equals K HgCl2 to the 1 and C2O4 negative 2 to the second order. Everybody see what I did there? Everybody see what I did there?
I don't like.
Okay, let's go back. I got people that don't know. We're gonna go back and explain it. All right, so is everybody okay where I got this rate law from the slow reaction? Everybody understand where this came from?
Yes.
Okay. Because if you go back and look at the reverse of that, this and this equals basically this, right? Because they're the same. So instead of writing this, because this equilibrium right here tells me to go reverse and forward, and that tells me this is an intermediate. So I'm gonna not write this in my rate law because this is basically equal to that. Does that make sense? That's it. So I rewrote it in there.
I have one question.
See, that's where I rewrote. See, right here. Okay. All right. So this came from the equilibrium reaction. So I said this equals this, and then I just plugged it in there, and then I had two of these. That's where this second order come from. Yes, ma'am.
I get where we got it from, but why? What's the difference between the first one and the other one?
Because it's going to be in the reverse reaction. Because it's at equilibrium, it can go forward or reverse. We just don't know. It depends what the value of K is. We haven't gotten that far.
But isn't the first one and the last one the same thing?
No. If you look at the first one,
Or the first rate versus the last rate law we made. Aren't they the same?
all right, so here's the rate from the slow reaction, right?
Yes.
We're good with that. All right, the top one above it,
Mm-hmm.
and it's always going to be an equilibrium above the slow reaction. That's the way they always write it. All right, so because we had this equilibrium here,
Yeah.
I can't write that into my rate, but I do know that this equals this. So all I did was take this and plug it in instead of that. That's it.
No, but I mean they're like the same. It's just a different way to write it. Is that what you're saying? Because they're
This and this are not the same.
but why would you write the other?
But they're not the same, but they're just equal.
Yeah.
Yeah, they're equal. That, just law of conservation of matter. These are my reactants, these are my products. They have to have the same number, right? It's organized different. They're
Okay.
not the same though. These are two totally different compounds.
Okay.
So this was part of my original rate, right? This and this. Okay? Well, because there's an equilibrium expression at the top of this, I gotta figure out which is the same. It could have been this one up here, and I would have replaced that with that. But it's not. This is what equals this if I go in this direction. That means this would have been the reactions, and that's what that means. It's reverse. It goes in reverse. So if this is equal to this, I can take this and plug it in place of that.
So I think that's my question. Why are we changing it?
Because it's at equilibrium. It's going in the reverse. It tells me that when I see these zeros here.
I think I'll get it after we actually do this more.
All right, it just means that it's going in reverse, so it's going in this direction, that's all.
Okay.
You have two of the C2O4 because
You had this
Yeah,
one
that one.
and then this one that replaced the other one. This equals all of that. So I just took this and dropped
Why am I
it
doing
down,
this?
and there's
Why are
two
we
of
doing
these
this?
at that point, that's why they're second order.
Okay.
Okay, it's just gonna take practice, guys, that's all. This is the first example. All right, so there's one more thing that I wanna go over with you guys.
Taylor,
It won't.
you're gonna get diabetes.
You're
You're
welcome.
gonna die.
All right, so
Think I have one?
we went over the potential energy diagrams, right? You guys can tell me exo and endo. And can you also tell me how many reactions? So that was Fridays, because I still want to do the evaluate, but I do want to pull up. Yeah. Yep. All right, so this is today's. Don't you wish you were there right now? I don't know. All right, so let's look at these graphs real quick, okay? These are some questions they may ask you. They may ask you if it's exo or endo, okay? Or they may ask you how many steps. How many steps would this one be? 2, right? You got 2 humps. Which is my slow step? The first one, right? Does that make sense to everybody? Why is that? Some people are not, I don't think it's making sense to.
It takes the most amount of energy.
Yeah, it's got the biggest hump, right? That activation energy is high. Remember, we're only as good as our weakest link. And I used the driving as an example. Y'all went off. You're like, oh, I hate when people are driving in the left lane going too slow.
That same day.
That's crazy.
I was like,
All right, look at this hot mess. How many steps? 4. Yeah. 1, 2, 3, 4. 4 steps to that. Which one is our slow determining step? What letter?
G.
I think that's a D. That's a Miss Jacobs D. Okay. So let's look at the evaluate from Friday. We didn't get to it, but let's look at it. All right, so this is a free response question. Go ahead and write this into your notebook. I'm gonna label it. You can put last Friday's date, which is the 6th on it.
I got hungry.
Got some stuff going on. All right, so this is a part of a free response question. I put Friday's date. Yeah, I put Friday's date.
Miss
Just part of
Jacobs,
Friday.
Miss Jacobs, could you make it bigger? Like the thingy?
This?
I
Yeah,
can't
can
see.
make it bigger.
Thank you. Thank you.
Ah.
I'm blind, guys. All right, so for this one, they want to know is, in the mechanism part F, which I cut off, is E a catalyst or an intermediate? Yeah, and it's not started, right? You know it's a catalyst if it starts with a reaction. It'd be up in here, right? This is an intermediate. Okay. All right, guys. Good job. All right. Let's go to section 2. Oh, okay.
I thought you said a problem will always start with the equilibrium.
It does.
Oh. Am I tweaking?
It didn't ask for any of that, though. It just asked for what if it was a catalyst or.
Okay.
I think we're showing all the steps out.
I would justify it. Oh.
You just say when it's not in the very beginning. That's how you would justify it. You would say it's not in the original reactants. Yeah. Yeah, it's not in the original reactants. That's how you know it's a catalyst. And that one says fast equilibrium.
Does that make any difference?
It just means it's fast. Yeah, you don't have to ask for band-aids. I mean, they're in the first aid kit. So. All right, guys, let's go to today.
talk about what we call molecularity. So looking at this, what do you see? This stuff's easy. So a unimolecular reaction, how do you differentiate bimolecular, termolecular? How do you differentiate it? Yeah, you look at your reactants. This is basically one reactant, two reactants, three. Pretty easy stuff, all right? So the products, the number of products doesn't matter. I got a quick little video. I think it's 1 minute.
Hey guys, it's Michael from Biochemistry. In this video, we'll quickly be going over what the molecularity of a reaction is. So for each reaction, we have to determine the molecularity, and the way to do that is to split how many reactants are present in each of the reactions. So in the first one, you can see there's only one reactant, so that makes the first one unimolecular. In the second one, you see there's one reactant and another reactant, so this will be bimolecular. And the next one, you see there's also one reactant plus another, so there's two reactants, so once again, it's bimolecular. And then in the third one, we have two reactants right here, and two reactants right here, so it is tetramolecular.
All right, so do you see
And
the
then the last
coefficients
one, we
make a
have
difference?
just two reactants, so this is another bimolecular. So when you're looking at the number, the last thing we have to take into account.
It wasn't stopping. What is going on here?
2A plus B, two react forms, so this is similar by taking into account.
Hold
So
on.
when you're looking at those that react,
Yeah,
so
it is.
two, you have to take in one,
Yeah,
and this total final one will have 2A plus B.
Okay, that was weird. All right, so I'm glad he did multiple examples because I was just about to show you that. All right, so you got to look at the coefficient because you got to remember this. There's literally two of these molecules that have to collide in perfectly to get to the product. Okay, so the coefficient does matter. Yeah, there's only one compound here. We got nitrous oxide, but there's two of them, so that's why it's bimolecular. Make sense?
Forms C, so taking into account the coefficients of the reactants, that we have 2 and 1, and this total of 3 things. So this is going to be termolecular. So if you have one reactant, it's uno. If you have two reactants, it's bimolecular, and 3 is ter, and then 4 is tetra. You're probably not going to see more than 4 reactants because it's really rare for 4 or 5 more reactants to collide at once.
If you want to learn how to ace chemistry, if you want to learn what's the best way to study for this class, if you want to learn some neat tricks and tips to take into your exam and do better in them,
I just see team.
All right, so let's get our notes.
How much they
Not very much. I'm just reading through. Oh. All right, so molecularity.
What is today?
It's just used to show collisions. Yeah. All right, so if we had A plus B given us C, we're just making stuff up here. All right, we're going off the dome. It's 1 and 1, right? So what would this be?
Bimolecular.
Bimolecular. If we had A given us B, what is that one?
Unimolecular.
Yep, unimolecular. What if I had 2A plus 1B given us C?
It's a termolecular. Ter.
Yeah, that's right, because there's 3.
Ter. He says ter.
Ter.
Good job, Campbell.
We knew what he meant, because I was going with try too.
Thank you, Mr.
All right, and then of course, 2A plus 2B giving us C plus D. That would be tetra, but we're not, I've never seen tetra, I've only seen it go up to 3.
This is it.
I know, it's turd, it's turd.
Why did Chem be different? Because Morgan, the people who were up until this point, we used try for everything, but the people who did
Because we do too much, that's why. We eat too much.
They hate kids, who just want
Is that the notes?
Morgan, you're the idiot.
That's it? Oh God, it's a miracle.
Wait,
It took up over 8 lines.
Ms. Jacobs, is that the end of the notes? Is that no more notes?
That's
That's it for today.
Oh.